Alright, so we're going to go ahead and continue from the previous video, this problem here. We're going to work on part B. So we need to find the volume of the solid generated when R is revolved around the horizontal line y equals 8. So if we look at our picture, it looks like this right here is y equals 6, so this is 0, 6. So it looks like I need to rotate it about some axis here. What I'm going to actually do is resketch my figure here. So let me go ahead and draw it really quick, or redraw it I should say. Alright, so there's my y-axis, and I'm going to sketch my x-axis here. And it looks like I have some curve that goes in this direction here. And then I have some horizontal line at 6, so here it is. And there's my region R. But they want us to get this region and they want us to rotate it. Let's say that this is 8. This is the line y equals 8. And they want us to take this yellow region here that you see, and they want us to rotate it around y equals 8. Well, what is that going to look like? Well, again, it looks like we're going to have some shape that does something like this. Excuse my horrible artwork here. Okay, so we'll have something like that. Notice that if I rotated it, we'll get that. But keep in mind, this is not a flat object. What we've actually done is we've added some type of I want to say spherical opening here. So we have some type of cylinder almost, or some type of, again, some type of spherical opening there. So we have some type of solid here. But I want you to take note that the middle part is hollow. Right? There was nothing in there. There's nothing in this middle part. It's just hollow. The solid region comes here. So the solid part is this space that you see here, and this part right here as well. This is also solid. Now what we want to do is find the volume of this thing. So what I can think about doing, just like in the previous videos involving volumes and disks and stuff, what I can actually do is I can think about maybe slicing it. I can think about maybe giving it a slice here. So let me go ahead and try and draw my slice here. So it's going to look something like that. And so what I've kind of done is draw some type of cylinder, and I'm going to label the width dx here. So let me go ahead and pull this out. If I pull out what I've just sketched, my slice here, it looks something like this. So I'm going to kind of draw it a little larger than what I have it in my picture, just so that it's a little bit more clear. So there's my dx, right? There's my dx, there's my slice, but it looks like it's kind of going to be a cylinder of some sort. So there we go. We have this thing that we've sliced out of our picture here. The only problem is that this part right here is hollow. So there's actually some type of open space here. So this is not a full solid cylinder. In fact, we have some open space here. So what we're actually dealing with here is a washer. Now I want you to pause the video and kind of think how you'd find the volume of this one washer here, or donut or tire like object. But I want you to really think how would you find the volume of this figure here, given that there's a hole in the center. Now, assuming you've paused the video and had some time to think about it, you might have the intuition, well, why don't you just find the entire volume and then just take away this center volume, and that would leave you with whatever remains. And that's exactly the idea. So what we're going to do, let me write it here. So I'm going to say that the volume of one washer. So we're only going to look at one washer. Our one washer that we have here is going to equal pi r squared times our height. That's the area, or I'm sorry, the volume of the entire one. And maybe I should do this in green so that it kind of stands out. So again, pi, and we're going to look at the radius and then h, again, that's just the basic formula for volume of a cylinder. But then we're going to take away the volume of the inside. Well, the volume of the inside is just another cylinder. Well, pi r squared h again. Now keep in mind that these two do not cancel each other out. You might want to think about this one as this is the radius of the outside, of the outermost function, and this here is going to be the radius of the innermost function. So I'll just call it r out and r in. So we have pi r squared, r out squared, times h minus pi r in squared times h. Again, referring back to this where we're talking about the inner radius, and then again talking about the outer radius. So here's the thing. H, if we look at our diagram, h is given by this dx here. So I can replace h with dx here. So that's what I'm going to do. I'm going to say that this is equal to, let's see, pi, we're going to have r out squared dx minus, and again the same thing here, h is getting replaced with delta x, so our dx here. So we're going to have pi r squared in dx. Okay, so our formula is starting to come together pretty nicely. I can even clean this up a little bit more. I notice that they both have a pi in common, so I can factor out a pi. I can even factor out a dx, and what I'm left with is r, let me try and stay color coded here. So I'm going to have r squared out minus r squared in. Again, I'm getting off here with my colors. R squared in. So again, the outer radius squared minus the inner radius squared. Well, now it's time to figure out what these radiuses are, and I think that's the most challenging part here, is trying to figure out what's your outer radius and what's your inner radius. Well, if we go back to the diagram, if we go back to our figure here, the outer radius is from the center where we're rotating from, all the way to one of the edges, right? So we can think about it like that. Well, or you could even look at it the other way as well. You can say maybe you don't want to go that way. Maybe you don't want to work in that direction, but you could always say that it's the distance from the center maybe to the bottom half of the curve. Let's do that. In all the previous videos we've always worked to the top. Let's just do the bottom half for fun. Well, if I look at the center here, the center part will extend all the way to the bottom curve. That's the radius of the outer. That's the radius, and I'm going to draw it here so you can see it. That's the radius. That's the radius of the outer cylinder here. Well, what is that radius, right? What is the distance from the center, from here to, say, I don't know, here, where we're at right there? Well, hopefully you have some type of intuition. For example, what if this was 2? What if that was 2? Let's say the height was given by 2. Then what would be the distance here? Well, you would say 6. And I'd ask you, well, how did you get 6? And you would say, well, it's 8 minus 2. And that gives me a 6. So my radius here is 6. But what if that wasn't a 2? So what if that wasn't a 2? And what if I change this number to, say, a 4? Then you would say, well, it's 8 minus 4, and therefore the radius is 4. Now here, we don't know what this point is. All we know is that this point is given by a function. It's given by some function, y. So the distance would be 8 take away y. But now what is this function here? So you would have 8 minus y. You'd say, oh, the radius is going to be 8 minus y then. But what is y? Well, if you go back to your problem here, you'll notice that the bottom curve has y equal to 4 ln of 3 minus x. So we can say that r out is equal to 8 minus 4 ln of 3 minus x. I'm going to go ahead and stop the video here and continue in the next part, and we'll finish off the problem in the next video.